5 to 10 seconds. That is it. That is your total time of useful consciousness if you're a pilot dealing with an explosive decompression at 35,000 feet. Seriously, you've got roughly 5 seconds to react before your cognitive function just plummets and unconsciousness completely takes over. Welcome to This Explainer. I am super thrilled to have you here today. We are going to be looking at the hidden, absolutely vital engineering that keeps airline pilots conscious, alert, and, well, in control when the air literally runs out. We're talking about the incredible science of cockpit oxygen systems. Let's get into it. Part 1. The invisible threat. Okay, so this brilliantly illustrates the basic physics of the problem. As an aircraft goes up, the atmosphere obviously gets thinner. Now, the actual percentage of oxygen in the air, that stays exactly the same at about 21%. But look at the atmospheric pressure. Down at sea level, we've got a nice, comfortable 14.7 pounds per square inch driving that oxygen right into our blood. But at just 18,000 feet, that pressure gradient is literally cut in half, down to 7.3 psi. By the time you reach commercial cruising altitudes, the pressure drops so low that the oxygen simply cannot be forced through your lungs and into your bloodstream. And that physical limitation leads straight to a terrifying physiological condition, hypoxia. It's basically the progressive oxygen starvation of your body's tissues. When your blood oxygen saturation rapidly falls below that 96% safe baseline, your brain just starts to shut down. We're talking about a rapid decay in cognitive function, you lose motor control, and your situational awareness is totally gone. Without supplemental oxygen, it culminates in a complete loss of consciousness. So, yeah, it's a literal life or death problem up there, and it requires a really sophisticated mechanical solution. Section 2. Demand and pressure systems. So, aircraft oxygen systems are basically broken down into 3 tiers, depending on how high the plane is flying. First up, you have continuous flow systems. These just steadily pump a constant stream of oxygen, which is, economical and simple, but it's pretty wasteful, and crucially, it's really only sufficient up to about 25,000 feet. Because commercial pilots routinely fly way above that, they need something much more advanced: diluter-demand and pressure-demand systems. Let's break down diluter-demand first. This system is brilliantly efficient. It conserves the onboard oxygen supply by only delivering gas when the pilot actually inhales, on demand. Inside the regulator, there's this specialized aneroid-controlled dilution valve, which is essentially just a small pressure-sensitive capsule. At lower altitudes, it mixes ambient cabin air with pure oxygen. But as the plane climbs and the cabin pressure drops, that aneroid expands, gradually closing off the dilution port. By the time the aircraft hits a threshold of around 32,000 feet, that port is completely shut, and the system is delivering 100% pure oxygen directly to the pilot. But what happens when you go even higher than that? Well, above 35,000 feet, even 100% pure oxygen isn't enough, because the atmospheric pressure is just too low to push it into your blood. That is exactly where pressure-demand systems take over. The regulator actively forces pressurized oxygen into the mask, literally inflating the pilot's lungs to a higher pressure than the surrounding cabin. It artificially creates the pressure gradient they need to survive. But here is the wild part. Because it's actively forcing air in, it reverses your normal breathing cycle. The pilot actually has to consciously use physical muscular effort to exhale against the positive pressure of the system. It's totally exhausting, but hey, it's what keeps them alive at those extreme altitudes. Part 3. The quick donning mask. Now, what's really interesting about this is the harness design. This is a full-face, quick donning mask. And if you look closely at those straps, they aren't just simple elastic bands. No way. They are actually a whole network of hollow, rubber-like tubes wrapped inside a protective textile sleeve, and they're connected directly to the high-pressure oxygen supply. This pneumatic engineering allows for an incredible single-motion memory item for the pilots. Here's how it actually works in an emergency. The pilot grabs the regulator with just 2 fingers and pulls it right from the stowage box. Squeezing the red clips directs 55 to 70 psi of pressurized oxygen straight into those harness tubes. They instantly inflate, stiffen, and expand outward into this big, rigid, oversized structure. The pilot can then just slip this expanded harness right over their head, even if they're wearing thick headsets or prescription eyeglasses, using just one hand. And the moment they let go of the clips, the oxygen vents out, and those tubes aggressively contract, vacuum sealing the soft silicone facepiece tightly against their face. All of this happens in under 5 seconds. It's amazing. So the crucial point here is what happens if the cockpit fills with toxic smoke instead of just losing pressure? Well, these regulators have an emergency overpressure knob. If you turn it, it totally overrides the demand function and just forces continuous, highly pressurized, pure oxygen into the mask. Even if a pilot has, say, facial hair that breaks that perfect silicone seal around the face, it doesn't even matter. The positive overpressure ensures that pure oxygen is always pushing outward, seeping out through any leaks. This flow completely blocks toxic smoke and gases from getting into the mask, which allows the crew to safely do their jobs and fly the plane. Let's zoom out and see how this builds into a much broader aircraft architecture. This schematic for an Airbus A321 shows that the flight crew's quick-on masks aren't just standalone units. They're actually part of a highly sophisticated, heavy-duty distribution circuit fed directly by a massive high-pressure gaseous oxygen cylinder stored securely on the aircraft. It's a really robust, dedicated system built entirely to sustain the pilots so they can fly the plane through a worst-case scenario. Section 4. Cockpit versus cabin systems. It's a pretty stark visual contrast, isn't it? On the left, we have the pilot's complex, full-face, pressure-demand mask with that crazy inflatable pneumatic harness. And then on the right, you see what the aviation industry sometimes jokingly calls the Dixie cup. That's the simple, yellow drop-down mask for passengers. It's just a basic, continuous flow mask, complete with an external reservoir bag and some really simple one-way valves. The reason for these two vastly different systems basically comes down to their ultimate purpose. Pilot systems rely on those heavy, high-pressure cylinders and complex pressure-demand regulators because, well, the pilots have to be protected from smoke, they have to communicate clearly with air traffic control, and they have to remain perfectly lucid to actually fly the aircraft to safety. Us passengers, on the other hand, we just need to survive a rapid emergency descent. Our system is way simpler. Pulling down on that yellow mask yanks a pin that triggers a chemical oxygen generator, often called a chlorate candle. That chemical reaction produces just enough continuous flow oxygen to keep passengers conscious for a few minutes while the pilot dives the plane down to a safe, breathable altitude, usually around 10,000 feet. It's this totally invisible lifeline that most of us never even think about when we board a flight. So I'll leave you with this final thought. The next time you hear that standard safety briefing about the yellow masks dropping from the ceiling, will you take a moment to appreciate the brilliant, pressurized engineering securely wrapped around your pilots' heads, keeping them awake, alert, and in total control at 40,000 feet? Thank you so much for exploring this with me today. It's been a blast.